In this section, we're going to look at static equilibrium. Static equilibrium. First of all, there are two kinds of equilibrium. There are two kinds of equilibrium. These are called translational equilibrium and rotational equilibrium. Translational and rotational. So we're going to look at these two kinds of equilibrium. Let's start with translational equilibrium. Translational equilibrium. Now, an object is said to be in translational equilibrium if it's either at rest or moving in a straight line with a constant speed. Okay, so an object is said to be in translational equilibrium. Translational equilibrium if it is either at rest, or moving in a straight line with a constant speed, or moving in a straight line with a constant speed. Now, what condition should be fulfilled for this to happen? Okay, it's basically Newton's second law. For an object to be at rest or to move in a straight line with a constant speed, the net force acting on the object should be zero. So the condition that has to be satisfied for this to happen is that the net force acting on the object should be zero. Net force acting on the object should be zero. So the condition of translational equilibrium is that the net force acting on the object should be zero. In other words, if the net force is zero, then the object will be in translational equilibrium. So the vector form of this equation would be, if you add up all the forces acting on the object, then it should be zero. Okay, so this is the vector form of the condition of equilibrium. Now, if you want, you can express the forces in the ij in terms of ij, and then you can use this vector equation, or you can decompose this into two algebraic equations, which are the equations for the x component and the y component. Okay, so in component form, now if a vector is zero, then the x component is zero and the y component is zero. Okay, so if the sum of these forces is zero, then the sum of their x components also should be zero. F2x plus F3x and so on should be zero. Similarly, the sum of the y components also should be zero. So this is the condition of translational equilibrium in terms of components. Okay, so you see from these two equations you can solve for two unknowns. And then we're going to look at rotational equilibrium. An object is said to be in rotational equilibrium if it's either at rest or rotating with a constant angular speed. Okay, so an object is said to be in rotational equilibrium if it is either at rest, if it is either at rest or rotating with a constant angular speed. With a constant angular speed. Okay, so what condition should be fulfilled for this to happen? Okay, the condition for this to happen is that the net torque acting on the object should be 0. Okay, net torque acting on the object should be 0. Should be 0. Okay, so if an object is at rest or rotating with a constant angular speed, then you can add up all the torques acting on the object and equate them to 0. So this implies if you add up all the torques acting on the object, this should be equal to 0. Okay. Now we're going to limit ourselves to one-dimensional problems, so we're going to have only one component. Okay, one-dimensional problems are problems where the object is rotating in a fixed plane. So in component form, we'll just have one component, so we don't have to distinguish between x and y. So in component form, we have only one component, which is positive for counterclockwise and negative for clockwise. So if you add up all the components, you should get 0. This is for one-dimensional problems. For one-dimensional problems. That is rotation in a fixed axis. Rotation in a fixed plane. In a fixed plane. All right. So the condition of rotational equilibrium is that the net force, the net torque acting on the object should be 0. If you know an object is at rest or rotating with a constant angular speed, you can add up all the torques and equate them to 0. Now we're going to look at torque due to weight. Torque due to weight. So how do you calculate the torque due to weight? Okay. Now suppose, let's say you have this lever balanced over here, and you have this object over here. So how do you calculate the torque is this object? Because you see this object extends from here to here, but we also need to calculate to use the distance between the pivot and the object to calculate the torque. So what distance do we use? If you take this object over here, this would be the distance. If you use this object over here, this would be the distance. So how do you calculate the torque due to weight? So let's try to look at that one. Okay. First, well, we have already defined the center of gravity. Let me define the center of gravity first, which is basically the center of mass of this object. Center of gravity, we can use x, maybe position vector cg over here. This is a point at which an object can be balanced. Is a point at which the object can be balanced. The object can be balanced. Okay. Now, suppose let's say we have this object over here, and let's say it can be balanced over here. Let's say the mass of the object is m. The mass of the object is m, Now obviously if it's balancing it, then this force should be equal to the weight, which is mg. Okay, so this force pulling up is balancing this object. Okay, now let's look at the torque. Well, the CD clearance balances the torque, going to be 0. Okay, but let's see 0. So let's see where the torque about this point over here. Okay, now this is going to act as the center of gravity, so which tell you this perpendicular distance over here is the center of gravity x cg over here, right? Now the torque due to this force, this balancing force, is in a clockwise direction and in a counterclockwise direction about this point over here, right? So the torque, this one, is the weight that's pushing up times this perpendicular distance xcg, which is the x coordinate of the center of gravity, maybe somewhere over here. Okay, how about the torque due to this weight over here? Well, we can divide this into small masses. Let's say we take this mass element over here, let's call that dm. Its perpendicular distance over here, let's say it is x. Okay, so this x is going to be different for different mass over here. If you got another mass over here, then it will be a different distance and so on. So what you can do is we can calculate the torque due to this one. Okay, let's call it d tau. Okay, so torque d to dm, torque d to dm will be d tau equals the perpendicular distance x times dm times gravitational acceleration. But and the tendency of this weight over here is to rotate the object about this point, is rotate the object in a counterclockwise direction, right? So you can put a negative over here as a counterclockwise torque. All right, so the net torque, you just integrate for all the masses over here. Okay, so the net torque due to the weight, net torque, let's say torque due to the weight, torque due to the weight, we just integrate over all the mass elements. So you've got d tau over here, that will be negative the integral of x dm and gravitational acceleration. Okay, how about the torque due to this, the torque due to the balancing force? The torque due to the balancing force, which is mg, balancing force, you see it's counterclockwise. Let me call this torque is the weight, and the torque due to the balancing force, let me call this F. Okay, that will be, it is the perpendicular distance, the x coordinate of the center of gravity, times the mass of the object times gravity. Okay, but this object is being balanced, so the net torque is 0. Okay, since it is balanced, net torque equals 0. Net torque equals 0, which means the sum of the two torques, the torque is the weight plus the torque due to the balancing force F equals 0. Okay, so that means this is the torque is the weight, x dm times gravitational acceleration, plus this torque over here, which is the x coordinate center of gravity times the mass of the object times gravitational acceleration equals 0. Okay, so that tells you this torque over here, these two are equal. So xcg times the mass of the object times gravity equals the torque due to the object. Okay, so this is the torque due to the weight. So it follows that to calculate the torque due to the weight, you can use this expression over here. You can assume as if the entire mass of the object is concentrated at the center of gravity. Okay, so the torque is weight is equal to the weight of the object times the x-coordinate center of gravity. So the implication of this is, when calculating the torque due to weight, you can assume, you can calculate if the entire mass or the entire weight is concentrated at the center of gravity. This implies the torque due to weight can be calculated as if the entire weight or mass is concentrated at the center of gravity, at the center of gravity. Okay, so that's the conclusion from this expression. This is the torque due to weight. Okay, that equals to the weight times the x-coordinate of the center of gravity, which means you can just assume the entire weight is acting or is concentrated at the center of gravity of the object, and that will give you the torque due to weight. All right. All right, now let's look at some examples. Example, suppose let's say we have the following lever. Let's say it's balanced at the center of gravity, like this. Let's say this is 2 meters. Let's say this is 2 meters. Okay, let's say now we have the following forces. Maybe we have this 10 newtons over here, and let's say this angle over here is 53 degrees. Maybe we have another 5 newtons over here, and then let's say we have a unknown force over here. It's called F. Okay, and let's say this distance over here is 0.5 meters. All right, so the question is, if the lever is uniform of negligible mass, so you don't have to worry about the weight, negligible mass, and is in equilibrium, calculate the unknown force F. The unknown force F. Okay, so we want to calculate this force F over here. We know that it's in equilibrium. Now, we have two conditions of equilibrium. We have translational equilibrium. That means you can equate all the forces and then add them up to 0. And the other one is condition of rotational equilibrium, which means you add up all the torques and then add them up to 0. Okay. Now, if you use the condition of translational equilibrium, you'll have two unknown forces. You see this? There is an unknown force over here, which is the force exerted by the fulcrum. Okay. Something like this. But if you use the condition of rotational equilibrium, the torque this force is 0 because acting at the point of rotation over here. Okay, so it's easier to start with the condition of rotational equilibrium because you can just eliminate this force over here because its torque is 0. Okay, so we're going to start with the condition of rotational equilibrium. Okay, so since in equilibrium the net torque equals 0, so since it is in equilibrium, the net torque equals 0. Okay, net torque equals 0. So let's give this names. Let's call this F1 over here. Let's call this F2, And as I said before, the torque, this one is 0, so we don't have to worry about it because distance for this force is 0. The distance between point of application of force and the point of rotation is 0, so we don't have to worry about this force. Alright, so we just have these forces F1, F2, and F. So you can say that the sum of the torque due to force 1 plus the torque due to force 2 plus the torque due to the unknown force equals 0. Okay. Now let's look at this one. This one is pulling down, so its effect is to rotate the lever in this direction, which is clockwise. Okay, so the torque of this one is taken to be negative because its effect is to produce clockwise rotation. So you can say that this is negative F1 R1 sine theta 1. Okay, how about this? This force is also having has a tendency of producing a clockwise rotation, right? So that's also negative. So you've got minus F2 R2 sine theta 2. Okay, how about this force? This unknown force over here has a tendency of rotating it in a clockwise direction about this point of rotation, right? So that is positive. So the magnitude of the force F plus a distance and then sine theta F equals 0. Okay, so let's plug the numbers. The magnitude of the force F1 is 10, negative 10. Its distance is from the pivot to the point of application of force, which is 2. And its angle is 53 degrees. Okay, so you've got the sine of 53 degrees. Minus F2, the magnitude of the force F2 is 5. So you've got 5 over here. Its distance is from here to here, which is 2 meters. So R2 is 2. And its direction is 90 degrees perpendicular. So you've got sine 90. And then plus the unknown force F. Its distance is from here to here. You see this is 2 from here to here. This is 0.5. So this distance over here is 1.5. So that's times 1.5. Its angle is 90 degrees. Okay. So the sine of 90 equals 0. Okay. So sine of 53 is 0.8. So you've got negative times 0.8, that's going to be negative 16. Negative 16. And then this is minus 10. Alright. Plus the unknown force F. This is 1. So this is 1.5 over here. Equals 0. Okay. So you've got the unknown force F times 1.5 equals 26. So the unknown force F is 26 divided by 1.5, or you can say 260 over 15 newtons. Okay, so this is the unknown force F. All right, now let's calculate this force. Calculate the force exerted. Calculate the force exerted by the fulcrum on the lever. By the fulcrum on the lever. Okay, so we want to obtain the force exerted by this object on the fulcrum. Okay, now we're going to use the condition of translational equilibrium. Okay, now we know all these forces, so using the condition of rotational equilibrium, we can calculate this force. We can calculate this x component from the x part of the condition of rotational equilibrium, and then we can calculate the y part from the y component of condition of translational equilibrium. Okay, so object at rest, object at rest or in equilibrium implies the net force acting on the object is 0. Okay, so we're going to use the component form, and this are, we have F1x plus F2x, and then you've got the unknown force. Let's call Fx over here. Maybe let's just call Fx. Fx plus the force due to the fulcrum equals 0. Okay, F is the force due to the fulcrum over here. This is force due to fulcrum. All right. Let's say F is force due to fulcrum. Due to fulcrum. Okay. All right. And then for the y part, we have F1y plus F2y plus Fy plus Fy equals 0. Okay. So we have to obtain the x and y components of each force. Okay. So let's start with F1. F1. What do you know about F1? Its magnitude is 10. Okay. F1 is 10. And its direction theta 1 is this angle 53 degree, but you know, to be technical about it, it's actually the actual direction of the force, which is 180 plus 53 degrees, which is 233 degrees, so you can say 180 plus 53. All right, so the components are, this force F1 is 10 times the cosine of this angle plus in the I direction plus 10 the sine of 233 degree in the J direction. Or if you just use this angle over here, you know, you just make this x negative and you make both of them negative. Okay, so this is basically equal to negative 10 cosine of 53 in the I direction minus 10 sine of 53 in the J direction. Okay, so this is cosine 53 is 0.6, so this is negative 6 in the I direction minus sine 53 is 0.8. It's going to be 8 in the J direction, which implies F1x is negative 6 newtons and F1y is negative 8 newtons. Okay, so we have these components. First, let's look at F2. F2, it doesn't have an x component. Okay, it just have y component, so we can simply write F2x is 0. It doesn't have a horizontal component, and F2y is simply 5, and it's positive because it's up. Okay, how about the unknown force? The unknown force, well, that one also doesn't have x component. Okay, so we see that Fx equals 0 and its y component is negative because it's down. Okay, so it's negative, and we just calculated it. It's 260 over 15. 260 over 15. Now we're looking for this, the x component of the force due to the fulcrum and the y component of the force due to the fulcrum. Okay, so let's go back to the x equation. The x equation is f1x plus f2x plus fx plus the x component of the force's fulcrum equals 0. Okay, so we just calculated f1x is negative 6, so this is negative 6, and then f2x is 0, that's 0. Fx is also 0 because it's vertical, this is 0 over here, and then plus fx equals 0. So the x component of the force due to fulcrum is simply 6 newtons. Okay, so do you see that? This force is exerting a force of 6 newtons in this direction, and this one has to balance it to the right with the force of 6 newton direction. Okay, now let's do the the y part. So f1y plus f2y plus fy plus fy equals 0. Okay, so f1y is this one, negative 8 newtons. Okay, that's negative 8. f2y is 5, this one over here, plus 5, and then plus fy is negative 260 over 15 minus 260 over 15 plus fy equals 0. Okay, so this force over here is we got negative 3 from here, so you take the other side, it'll be 3 plus 260 over 15. You take common 15 over here, that's going to be 45 plus 260, that is 305 over 15 newtons. Okay, so these are the x and y components of the force due to the fulcrum. All right, so these are the x and y components. So we have, these are these forces. We have fx over here going this way, we have fy going this way. Okay, this is fx, this is fy over here. Now if you want to calculate the magnitude and the direction of this force, then we can say F equals square root of fx squared plus fy squared, and that is square root of 6 squared plus this force over here. Okay, and the direction would be tan inverse of fy over fx. That will be tan inverse of the y component, which is 305 over 15, divided by the x component equals 6. That'll give you the magnitude and the direction. All right. Another example. Suppose we have the following non-uniform lever. Let's say to get the scener and scener as you go to the other side like this. Let's say it's a non-uniform lever over here. And let's say it's pivoted at its center like this. Okay, let's say this distance over here is 1 meters, and this distance over here is 1 meters. Okay, now suppose we have a weight of, let's say, maybe 40 newtons acting at this end. Okay, let's say the mass, the lever shown is non-uniform, which means its center of gravity is not located at the center, and let's say has a mass of, let's say, 2 kilograms. 2 kilograms. Okay, the question is determine the we'll make this maybe 6 kilograms. 6 kilograms. Determine the location of its center of gravity. Center of gravity. Okay, now we know that the weight of an object can be assumed to act at the center of gravity, right? So let's say the center of gravity is located over here. So the weight will be acting at the center of gravity like this, the weight of this lever, right? So this is what we're trying to find out. So let's say this is x. Okay, so we want to find out how far away from the pivot the center of gravity is. Okay, all right. And not mention the lever is in equilibrium. Okay, the lever is in equilibrium. So you see we have a clockwise torque exerted by this force and a counterclockwise torque exerted by this force. So these two forces should balance each other if it's to be in equilibrium, right? So you've got the weight, which is a distance of x over here, equals the force, which is 40 newtons, times 1 meters. Okay? And the weight is mass times gravity. Okay? The mass we're told is 6 kilograms over here, and gravity is approximately 10, so the weight is 6 times approximately 10, that is 60 newtons. Okay? So W6 newtons, therefore we have 60 times its perpendicular distance x equals 40. It turns out x equals 40 over 60, or 2/3 meters. So the center of gravity is located 2/3 meters to the left of the pivot. So the center of gravity, this means the center of gravity is located 2/3 meters to the left of the pivot, to the left of the pivot.